Good afternoon, guys. This is the Blackbody tutorial video. This is a half lab. It's not difficult. It requires a couple of mathematical calculations, but it's very straightforward. This will allow you to investigate and study and confirm some of the ideas of blackbody radiation, Wion's law, the energy of a photon, the electromagnetic radiation energy, the usage of the Planck constant, and the blackbody curve. So at the beginning of the course, or in the first few weeks, we're going to start talking about spectral types of stars. So you don't really need to know in depth a lot about the spectral types. In fact, you will be using stellarium to investigate that and then corroborate in this table what you get using the blackbody curves, so Planck curves. So what you see here are different blackbody radiation curves that we can obtain by measuring radiation from the stars, right? We have different instruments that we can use for that, and we're able to plot intensity as a function of wavelength. Now, again, I don't expect you guys to know in detail what all that means. However, just as a general review, every star that we observe, the Sun, Alpha Centauri, Betelgeuse, Rigel, Antares, Alnitak, right? All those stars, they can be, their intensity can be plotted using the blackbody curve. Now, this shows you the ultraviolet catastrophe, right? In classical models, as you go farther with wavelength, you will get a higher intensity or luminosity. That's not the case because you have an inflection point here. And then you have the curve coming down. Now, different stars, they have a different skew. And that depends on their color and surface temperature. The peak that you observe here is what will give us a good approximate value for the surface temperature. All right. In the case of the sun, that's approximately 6,000 kelvins, by the way. Anyway, so I want you to pay attention to this equation. By the way, this should be 10 to the power of 6. All right. So the first part is pretty straightforward. You can either print or you can do what I'm going to do right now. So you have this spectral, this blackbody curve, luminosity as a function of wavelength. You don't care about this. You care about the wavelength. The first column is to find the wavelength at the peak on each of these stars, of each of these stars. So you can zoom this, and then you are going to use a straight line. And that's why I'm saying this is an approximation. Oops, sorry. That's not what I want. I want the straight line there. There it is. So the peak lands basically halfway, right? Half between 50 and 100 is 75 nanometers. You see the units? So 75 nanometers. So that's the wavelength at the peak. So you will write here 75 nanometers. How do you get the surface temperature? You're going to use this equation. Now, how do you use that equation? You are going to bring your calculator and you're going to do this. 2.898 times a million, right? Divided by 75, 38,640 kelvins. So that's what you write here, 38,640. In fact, let's actually write that in here so we don't 38,000. Let's take a look again, 640. So 640. And then we're gonna estimate the spectral type. Now, how am I going to do that? Right? We're going to do that by looking at this. Look, this is where you have to be careful. They give you these spectral types. But between O and B, B and A, there are 9 subtypes. O1, O2, O3, O4, up until O9. So you have to be pretty accurate. You see that the range of values, there's a jump, especially here. Look, there's a 30,000 Kelvin jump. So that's a lot. So what you're going to use to estimate the spectral type, you are going to use this one here. So we have this temperature. You see you have 33,000 for B0. Now, the maximum temperature for each spectral type, O, B, A, F, G, is going to be on 0. And then the lowest one will be on 9. So for example, O0 will be 60,000. O9 will be approximately 34,000. Right. Actually, probably even more. It's a range. So you can go from 37 to 35,000 actually. Because you also have 8.5, 9.5, by the way. However, we normally tend to use integers for the subclassifications. All right. So for 38,640, I will estimate approximately a 08 or 08.5, maybe 09. All right. But it cannot be 03 or 2, right? Because that's in here. It cannot be 05, obviously. So it has to be between 05 or 09. It cannot be 06. It's too close to 46,000. So it will say 08 or 09. So that's what you will write here. Here is the nice part. You can check your estimate using Stellarium. All right. So you're gonna get your Stellarium. You look for the star Alnitak. That's the star that I used. And then you look for the spectral type. And look what I get. 09.5. I said 08.5, 09, right? So not bad. It's a good estimate. Why is it not perfectly precise? That's because we are using the Blackbody curve to get this temperature, to get the wavelength and then the temperature. So obviously there's gonna be some error. All right, that's just how science works, guys. However, it's a very good estimate. Now you're probably wondering, how do we know the real value exactly? Because we have other techniques, like for example, spectroscopy. All right, to measure magnitudes, and you're gonna learn that later in the course. In fact, the next lab we're gonna be dealing with magnitudes more. For now, we're just looking at the black body radiation. So you do the same procedure I just explained for the other stars. Be careful when you have curves like this, because that will give you more room for error. This type is very easy. This one as well. This one is not so bad. This one is not bad. But be careful when you have such a large peak like this, because the precision will decrease. All right, the same here. But guys, I'm not gonna be grading that you get a perfect estimate. I'm gonna be grading this and make sure that you are actually doing this right. As I say, it's a very straightforward lab, and I'm pretty sure you guys can finish it on the first day that we do this in class. I'll see you guys later, and I hope you guys have a nice day.